Start recording. A plank of 8 meters, mass 10 kilograms, rests in equilibrium on two identical chairs. Chair A is placed 1 meter in from the end of plank. Chair B is placed at the other end, as shown in the diagram. The chairs can provide a reaction force. Now, you guys know all about reaction forces, right? What's a reaction force?
Opposite to equal.
Yeah, so it's equal and opposite to whatever is happening. So the only forces we've got acting downwards is the mass of the chair. Yeah. So we have reaction forces at B, and we have reaction force at A counteracting that. So what's going to happen? It says the chairs can provide a reaction force of 50 Newton meters before breaking. Assuming that the plank can be modelled as a uniform rod, G is 9.8, determine if either chair will break. So when will a chair break?
When it's 50.
Yeah. So the reaction force of the chair, if it's greater than 50 Newton meters, the chair is going to break. Okay. So what forces do we have to take into consideration? Well, obviously we've got the mass of the rod. Is the mass of the rod just going to act straight down on both chairs?
No.
No. Good. Why not? What's happened?
Because chair A has an extra meter in length.
Okay. Yeah. The chair A is slightly inbound. So, are there any moments involved?
Yeah.
There are. You think about it. Chair A, look. What's the force acting on B? Is the force acting on B purely a downwards force?
No.
What is it?
It could be a horizontal force since A's got more.
There's no horizontal.
Vertical.
It's where's that according to you? Clockwise? Yeah. Because the chair A is a pivot point when you consider chair B, relative to chair B. Right? So therefore, the force being applied on B is actually a moment about A. That makes sense? Okay. What about chair B then? So, is there force being applied on chair A? Yes. Okay. Another moment. Yeah. The mass, the weight is pulling down, but this time in the anti-clockwise direction. All right. So, we are looking at reaction forces counteracting the moments, not just downward forces. So we have this diagram. Okay. I've not quite completed it for you, but you can draw it in your books. So I've simplified the diagram. Look, I've got chair A, chair B, the reaction force at A. Oh, would you like a book or just a bit of paper or something? Do you want to write? Yeah? Just a bit of paper rather than the entire book. That'll be it. Step down. I know Jacob's not writing anything down. He'll come to me next Wednesday and ask me to write it on the forum. Okay, so we've got I'm taking moments about A first. All right. So I've got 3 meters times 10g. Why? So 10 kilograms times g is 9.8. And why have I done 3 meters times 10 times g? What is that?
That's where the pivot point is from A.
So that's the moment, yeah? So this is the moment about A. Force times distance. So this force, distance from A. All right? Why is that equal to 7 times the reaction force at B? Because it's in equilibrium. Okay? Force times distance. So we've got 7 meters away from A. Okay? And the reaction force is going the other way, so they have to be equal to each other. Right? So I've rearranged that to do the reaction force at B is therefore 3 times 10g divided by 7. Make sense? Rearranged it. Over to you. You work that out. So yeah, you should have found that. Switch not too much.
Just 42 newtons, right?
Yeah, just 42 newtons. So you found that this is 42 newtons, which means reaction force at B is 42 newtons. The chairs were okay up to 52 newtons. So 42 is less than 50 newtons. So chair B, good to go. We're fine. Right. You can see here there's two methods. I'm not showing you what they are yet. Moments about, sorry, bar, go out there. Moments about B, and there's an alternative method. Have a go, because it's a good bit of practice. Do the moments about B now to practice, and think, was there a quicker, hence the star, method that you could have used?
Is it in equilibrium?
Yes, but well, it is. We're told it is, but we're trying to find out whether both chairs are going to be okay.
Mm.
We think chair B is going to be fine. But what about chair A?
That's the alternative.
So we can divide by 7.
No. Some of. It's just both of them are that way, and this one's that way. So if
Which
it's-
one?
If they're in equilibrium, then they need to add up together.
Which one do you think? So what is this?
Chair A.
What's- Why have I got 3 times 10g? Because I've done moments about A, yeah? So the mass is 3 meters from A. What if I take moments about B? So it's actually going to be 4. This rod is 8 meters long. Yeah.
7 minus 3.
So 7 minus, yeah, 7 minus the 3. So this is 4, isn't it? This is a distance of 4. So we would have 4 meters times 10g is equal to what times RA this time? Yeah, still 7, isn't it? Because they're 7 meters apart.
It's not okay.
Eh? 56 sounds right, yeah. So we think chair A is breaking. Anyone thought of quicker methods?
10 times 10g, which is just the total force minus the 42 newtons that you ordered them, gives you 56.
Yeah, exactly that. So moments about B, 4 meters times 10g, 7 meters times reaction force A. Rearrange it, you do get the answer 56. Okay, 56 newtons. But as Reggie was just saying, like you were doing earlier on in the course, this reaction force A and this reaction force B are directly against this 10g, right, acting in opposite directions. Therefore, we can state that RA plus RB must be equal to the 10g, right? We already knew that RB was 42, and this is obviously 98. So RA plus 42 is 98, therefore RA must be 56 newtons. So that would be obviously a quicker way to do it. Okay. Make sense? Shop sign is formed from a rectangular plastic sheet. Weight 40 newtons. It's held in equilibrium by a vertical wire at A and horizontal wires at A and C. So you've got 3 forces acting with the wires, and we've got a 4th force, which is the weight, yeah? So we've got to see if the sign can be modelled as a uniform laminar. Let me just, because this often comes up and maybe we don't talk about enough in class. It says here, if the sign can be modelled as a uniform laminar, blah, 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 blah. And then maybe the last question, what would be one limitation of this model? Okay.
That's not uniform. One side of the sign.
Yeah, often signs are not uniform laminars, are they? Might have a ridge round a bit of it, or you know, it might have some rust. You never know. It says plastic sheeting, so it could be not too bad, but that might be a potential problem. That's the kind of thing they're looking for you, just to say, what if it's not uniform? Right. So we've got to find those tensions, the forces. So how do we go about doing that? Take moments about A. Okay. So I've got my clockwise moment is 0.25 times 40. Why?
Because the moment in the centre is 40 and the centre is 25. The edge.
So we're talking about moments on A, yeah? Moments about A. So remember, it's the line of acting of the force. The force is this line here. So we're looking at this distance. So that's your 0.25. Okay. Why does that equal 0.4 times T3?
It's going in another direction.
Yeah, because it's going in the opposite. This one is obviously, you can kind of see it by the line I've drawn. That's going to be a clockwise rotation, but T3, obviously, if this is the line of action of that force, we take the distance from A is that distance, which is the 0.4. Obviously, that looks like an arm going in the opposite direction. And why are they directly equal? Because it's an equilibrium. So T3 is, well, you can work out T3. All right. Question for you. Why did we start with taking moments about A and not about a different point? I'm going to ask you, because this is very quiet moment, I'm going to ask you, you can write that down. I want you to answer the question, why A and not C, or why not B or D? All right? Why A? Discuss it with the person next to you, and then you can tell me your answer. By starting at, I'm going to, my laser thing, I should stop. By starting at A, okay, if I'm taking moments about A, these two forces are 0, aren't they? There's no moment, because the distance is 0 from that point. Therefore, this is the only force applying a moment about A. If I decided to do about C, obviously T3 is eliminated, but I've got 2. And I'd have this up here, this formula, to some extent, but it would have 2 unknowns in it. If I did it around D, I'd have 3 unknowns. So it is as simple as, when you look at the problem, think, how am I going to be able to solve this? I've got to try and resolve something. So I started with moments about A because that enables me to work out T3. What did you work out T3 to be?
25.
25 newtons. Okay, Newton, is it Newton meters or just newtons? What?
No.
It's not. It's newtons because T3 is just the force.
Oh, yeah.
0.4 times T3 would give you the Newton meters. Okay? So how do we then work out T1 and T2?
That T1 and T2 is equal to T3.
T1 plus T2 is equal to T3.
Yeah, but in equilibrium.
Okay. The equilibrium idea is right, but not T1 plus T2. What are equal to each other?
Which ones are
T3
missing out?
T3 and T2.
T3 and T2 are equal, aren't they? Because they're acting in opposite directions on the same line. So we can say T2 equals T3 because they're horizontal forces, and T1 is equal to the weight because it's a vertical force. So therefore, because we've got T3 is 25, T2 is 25 newtons, and T1 is 40 newtons. Straight into it. Okay? Seems like a super easy way to finish that question. All right. So that's just taking your moments to a little bit further than we were yesterday.